In any operational system, resources, time, and capacity are strictly finite. Achieving high speed, low cost, and perfect quality simultaneously is a physical impossibility. Operational leaders engineer deliberate compromises to navigate these constraints. This logical framework is known as trade-off theory. This framework allows leaders to design a network that aligns their inherent logistical limits with the specific value their customers expect. Market leaders succeed by identifying and accepting specific operational compromises that support their business model. Amazon Prime, for instance, prioritizes speed and service. This requires them to absorb high logistics costs to guarantee rapid delivery. Walmart uses a different model, prioritizing low cost through a regimented distribution network that keeps retail prices at a minimum. Zara focuses on market responsiveness. They maintain excess production capacity close to their retail markets, allowing them to shift designs mid-season while accepting higher manufacturing costs as a result. Strategic success requires an explicit decision regarding which performance metrics to prioritize and which to deprioritize. The formal definition of trade-off theory states that improving one supply chain objective typically requires sacrificing another. The manager's primary directive shifts towards finding the optimal balance among these competing goals. We can observe how this dictates operations by mapping the relationships within specific supply chain scenarios. Consider the tension between inventory holding and service level. Higher inventory volumes provide better product availability. This creates an immediate financial requirement: higher holding costs. As service levels rise, inventory costs must also rise. Geographic warehousing follows the same logic. Centralized warehouses lower inventory cost, but increase delivery times. Local warehouses enable faster delivery, but duplicate inventory. Thus, customer responsiveness increases overall inventory costs. Similarly, large production batches lower unit costs, but reduce flexibility. Every operational choice creates a corresponding penalty in an opposing performance category. These scenarios map to a universal structure that dictates the design of industrial networks. This table of typical competing objectives shows the persistent dyads that planners must navigate. Improving efficiency impacts responsiveness, just as increasing speed raises transportation costs. This persistent tension between cost and responsiveness serves as the foundational balance point. These trade-offs are completely universal because they are deeply rooted in the physical limits of the modern global economy. 5 unyielding constraints impose these limits: finite resources, facility capacity ceilings, uncertain customer demand, transit need times, and fixed economic cost structures. Misinterpreting these constraints often leads to a common systemic failure. This is known as local optimization. If purchasing minimizes price by buying in massive bulk, and logistics minimizes transport costs, while production maximizes utilization, each department appears efficient. But when every department maximizes its isolated metric, the total supply chain performance declines. The bulk purchasing that saves unit cost creates a spike in warehouse holding costs. The individual departments grind against each other, fracturing the main system. Managing these trade-offs requires global optimization, where the end-to-end performance of the network takes priority. The health of the entire system must override the peak efficiency of any single department. Managers apply these theoretical constraints during specific planning phases. During network design, planners determine the optimal number, location, and capacity of warehouses. For inventory policy, they weigh safety stock against customer service level. Finally, for transportation strategy, they choose freight modes and shipment frequencies, balancing cost with delivery speed. While these constraints are real, they are not necessarily permanent. A common misunderstanding is that trade-offs require a permanent performance sacrifice. In reality, technology and innovation shift the entire trade-off curve. Targeted investments in automation, real-time data, and forecasting allow companies to reduce friction and improve multiple metrics at once. We can summarize the absolute rules of the theory in 3 points. First, strategy balances compromises, not single indicators. Second, global optimization overrides isolated efficiency. Third, balancing cost and responsiveness is the foundation of network mapping. True supply chain mastery lies in engineering an interconnected system of calculated compromises that fulfills a specific